Hi, I'm Tom St. Lawrence, President of American Holt Corporation. We put together a video for you that showcases our facilities and procedures for reverse engineering, high quality, readily available aftermarket parts. With highly skilled employees and over $1 million invested in metrology equipment, we have the serious capability to uphold our commitment to produce products that will satisfy any customer. Let's take a look at how we operate at American Holt.
In the world of reverse engineering, accurately identifying materials is critical to creating successful parts. Small differences in material composition can have significant effects on strength, corrosion resistance, and other important properties. The most common parts we reproduce are made of metal. For these, we utilize X-ray fluorescence technology, or XRF, to obtain precise material readings. The XRF device uses X-rays to measure an object's elemental composition, which is compared against an extensive materials library to identify the exact materials used. Our portable XRF can be used on samples of any size or shape, produces results in seconds, and is completely non-destructive. The metallic components we test are most commonly copper alloys and alloy steels. However, the XRF cannot detect light elements such as carbon. For materials with lighter elements, like carbon steels, we employ our optical emission spectroscopy system. The OES system utilizes a high-energy arc to vaporize a small portion of sample material. For parts made from organic materials, including plastics and rubbers, we rely on our Fourier Transform Infrared Spectroscopy Unit, or FTIR. Samples are placed on an optical crystal and exposed to infrared light, which causes the sample to emit energy. This unique energy signature is matched to a corresponding signature in a materials library. Like the XRF, the FTIR is completely non-destructive, and results are fast, meaning that valuable customer-supplied samples can be returned quickly and undamaged. The cutting-edge technology of 3D scanning has multiple applications in American Holt's reverse engineering process. We utilize the Faro Design Scan Arm. The scan arm features 7 degrees of freedom, or points of articulation, a scan accuracy of 75 micrometers, and a point capture rate of 500,000 points per second. To translate, its primary application of laser scanning allows highly accurate geometry capturing of parts with irregular, rough, complex, or organic features often present in castings. The scanner features a large range of operation, with the ability to capture both small and very large objects. As the hardware scans the parts, the data is captured by Geomagic Design X software. This software can combine multiple partial scans, measure geometry, perform deviation analysis between scans, or between scans and CAD models. These scans are then used as reference in the construction of CAD models, which in turn are used to create engineering drawings, all serving the purpose to ensure dimensional accuracy. In addition to reverse engineering, we also utilize the scan arm for quality control. Parts received from vendors can be scanned and compared against CAD models to ensure the parts were manufactured correctly. At American Holt, we utilize 3D printing technology for a variety of applications, including casting, fixturing, and prototyping. We apply both FDM and SLA printers in our workflow. FDM, or Fused Deposition Modeling, is a ubiquitous method for desktop 3D printing. It functions by melting spools of plastic filament and extruding the plastic onto a flat surface to build up an object layer by layer. FDM printing is highly versatile, can accommodate a wide selection of printing materials, and is relatively inexpensive to operate. SLA, or stereolithography, is the oldest form of 3D printing and is used in many high-precision applications. Prints are formed by exposing liquid resin to light in order to harden. Like FDM, these prints are built up layer by layer. SLA printing can have very high resolution, which enables parts to be printed with extremely fine detail and to have notably smooth surface finish with little post-processing. The prints also tend to have good engineering application due to their isotropic nature, making them equally strong in all directions. A primary use of our 3D printers is small batch investment casting. Investment casting involves creating a pattern out of sacrificial material, which gets coated in ceramic and then burned away to create a mold for molten metal. Our FDM printers are used for this process due to their ability to quickly print hollow patterns with specialized material that will burn away easily, all for a low cost. Both our FDM and SLA printers can also be used to generate reusable patterns for sandcasting processes. Engineering materials also allow us to develop functional prototypes. Using 3D printing allows for quick iteration in the design of a part. High-detail prints can be used to check how a new design will fit amongst existing components. Prints made from specialized materials can mimic how a final product would perform under realistic loading and environmental conditions. When reverse engineering products, it's critical that the parts produced are able to hold up to their intended application. Having parts that are properly toleranced and made out of the correct material is necessary to achieve ideal functionality. However, there are still additional factors involved in ensuring that a part performs as intended. Secondary treatment processes, such as heat treating and curing, can alter a component's physical properties, such as hardness or strength, which can make critical differences in a part's performance. This is why American Holt devotes resources towards verifying the mechanical properties of all parts we produce. One of the most significant properties we check for is hardness. A part that is not properly hardened can deform and easily wear down. Our main tool for hardness testing metal parts is a standard Rockwell hardness tester, able to accurately measure the hardness of materials from hardened tool steels to soft brasses. This tester functions by applying force to the surface of a part through an indenter. The shape of the indenter and the amount of penetration is used to determine the hardness of the part. For parts too large to fit in the standard hardness tester, we have portable hardness testers, which allows us to quickly and accurately measure hardness. These include our clamping dial hardness tester, and for very difficult to reach areas, a digital drop hardness tester. Plastic and rubber components are typically much softer than metals, and are often measured on the durometer scale rather than Rockwell. For this, we have a micro hardness tester, which measures penetration depth of an indenter on a smaller scale, and with higher repeatability. For parts too large to fit on this tester, we also have handheld devices. Springs are a common component produced at American Holt, and one of the critical aspects of a spring is its stiffness, or spring constant. For determining this vital characteristic, we utilize specialized spring testers. The amount of force required to deform the spring is shown to the user. Dividing the force value by the distance provides the spring constant value. We have testers specialized for small force springs and heavy-duty large force springs. Both are able to take measurements for compression and elongation. The surface roughness of a part does more than determine how shiny the object is. Roughness is a direct contributor to surface friction. To measure this characteristic, we employ a profilometer. The profilometer has a precision ground stylus that moves over the surface of a part, measuring the small peaks and valleys that are developed during the machining process. The profilometer then correlates that information and provides the surface roughness of the part in values of micro-inches or micrometers. Every machinery part has its own specific geometry and manufacturing requirements. Some have complex geometry, with tight tolerances that require specialized knowledge and equipment to reverse engineer. Gears are ubiquitous pieces of equipment with very specific shapes. The geometry of gears in modern machinery conform to various standards that allow interchangeability and maximized efficiency. However, There are still a large number of different gear types, some with very similar geometry, which means many criteria have to be examined in order to fully identify a gear's specifications. We successfully reverse engineer a wide variety of common and uncommon gear types, including straight bevel, spiral bevel, spur, and helical gears. For most gears, we can quickly and accurately measure gear features with handheld tools. Once measurements have been taken, we utilize specialized software to verify what standard the gear conforms to. For gears with more advanced geometry, such as helix gears, we employ our more advanced metrology equipment, like the Faro Touch Probe Arm, in order to determine pitch angle and other specifications. For truly unique and non-standard gears, we make use of an M&M analytical gear inspection machine. When all the necessary information is collected, we can generate a CAD model of any gear with precise teeth geometry, ready for manufacturing. While similar in appearance to gears, splines transmit rotary motion along a single axis. Splines also have less versatile roles than gears, which means they are less varied and therefore easier to identify. Our large collection of spline gauges allows us to quickly verify the identity of a spline with few measurements. More challenging to reverse engineer than gears or splines are cams. Like gears, cams come in a variety of designs such as barrel, open-ended barrel, or ring cams. However, unlike gears, there is no standard geometry for a cam. A cam functions as a guide for a roller. The shape of the cam is dependent on whatever unique set of motions the roller is intended to go through. Precise roller movement requires tight tolerances on the cam surface, and the shape must be mathematically tailored for proper accelerations. In order to accurately capture this critical geometry, we collect displacement values on the roller, paired with angle of rotation values on the cam. Plotting the displacement with the angle allows us to build a profile of the cam. The profile can then be tailored based on mathematical principles to ensure it performs as intended. Finally, a drawing and solid model can be created for the cam, readying it for manufacture. Features on a part can be measured in a variety of ways. Successful reverse engineering requires identifying how to accurately measure components while minimizing time and cost. Hand tools and measuring instruments are an ideal way to quickly obtain precise readings without needing to employ larger and more advanced systems, such as a CMM. We maintain an extensive collection of hand tools suitable for any measurement application. Calipers, or more specifically vernier calipers, are a staple of many engineering arsenals. Their versatile design allows them to measure the length of a wide range of features. Calipers will typically have an accuracy of 1/1000th of an inch, which is sufficient for dimensioning most machined features. If greater dimensional accuracy is needed, micrometers are the next up. With precision 10 times that of normal calipers, micrometers are used to measure critical features, such as the diameter of mating shafts. The design of standard micrometers lack the versatility of calipers, so there are often specialized versions for different applications, such as depth micrometers for measuring blind distances, and internal micrometers, or trimix, for measuring bore diameters. Fairly specialized yet incredibly useful, the plating thickness tester measures the amount of covering applied to a base material. It is most commonly used for chrome plating, nickel plating, and paints. In addition to reverse engineering, the tester can also be used to ensure coatings have been applied evenly over the length of a part. Our collection of gauge pens ranges from 6/1000ths of an inch to 1 inch in 1/1000th of an inch increments. The pens are used on critical holes to both qualify hole diameter and provide the engineer with an idea of how the mating parts will interact with the hole feature, such as a slip, press, or intermediate fit. Gauge pins can also be used where normal measurement equipment cannot reach. Radius gauges are used to roughly approximate non-critical radii on the surface or edges of a part. These radii are typically non-functional and are more for aesthetics or to round sharp corners for safety. Thread gauges are utilized to quickly assess the type of thread on a part and are available for both internal and external threads. These gauges may evaluate the size of the thread as a whole, but for larger threads, thread pitch and diameter may need to be measured separately to find the thread size. Tightly controlled, these gauges provide far greater certainty than checking threads against stock screws and bolts, as some metric and imperial threads are almost identical. While handheld tools can quickly and accurately measure the dimensions of a part, the size, complexity, or quantity of parts often require the use of larger and more advanced measurement equipment. We make use of some of the most advanced metrology systems available in order to inspect and reverse engineer parts with high amounts of accuracy and efficiency. A height gauge is used to measure the linear distance between features on a part. Its fast operation makes it ideal for quick inspection on multiple components. Multiple probes allow flexibility in what features can be measured, such as small or hard-to-reach surfaces. Extremely large parts can also be measured, depending on the size of the gauge. Digital gauges can connect directly to computers for quickly capturing and analyzing large amounts of data. A coordinate measuring machine, or CMM, is used to measure the location of individual points in 3D space. A probe with a hard tip, such as sapphire, makes contact with the surface of an object to measure its location. The versatility of a CMM makes it ideal for measuring objects with large amounts of complex geometry. On a manual CMM, an operator moves the probe by hand, controlling individual axes of motion independently. Setup time for a part on a manual CMM is minimal, and programming is not required, making it a quick and effective way to check the geometry of parts in small quantities. For an automatic CMM, all degrees of motion are actuated electronically, including probe orientation and tool changing. Movements are programmed by an operator and can be iterated any number of times. With proper setup, this allows large volumes of parts to be quickly measured and inspected. Post-inspection, reports can be automatically generated and saved for future quality control reference. Video inspection systems utilize magnifying optics to produce an undistorted image at a known size. This means that the dimensions of objects in the image can be measured accurately in very fine detail. Video inspection systems are especially useful for measuring parts with geometry that is awkward to measure on a CMM, or whose shape may change when pressure is applied to them, such as a rubber O-ring. Some systems even have the ability to automatically identify geometric features. Center testers are utilized primarily for inspecting variation on cylinders with multiple diameters. Typically an analog system, center testers are easy to set up and utilize two indicators to measure variation around the surfaces of a cylinder. An operator uses these readings to compare how one surface deviates from another. 3D scanning technology is a powerful tool used to digitize the surface of any object. There are many methods for 3D scanning, but we utilize a laser scan arm with an accuracy of 75 micrometers. Paired with powerful analytical software, 3D scanning allows for detailed part inspection and streamlined reverse engineering. Reverse engineering is often a complex task, demanding a large number of different processes. Many of these processes require computer software to perform efficiently. As a result, a robust collection of engineering programs is needed for a successful reverse engineering operation. We utilize a wide array of software in our workflow in order to meet any engineering challenge. Out of all the computer-aided design or CAD software on the market, SolidWorks is an industry standard and market leader. A large suite of modules makes SolidWorks a robust tool for many steps in the engineering process. In our engineering workflow, SolidWorks is primarily used for creating models of physical components. Parts are measured physically and then replicated with parametric modeling. If an object is composed of multiple parts, models can be combined to form assemblies. Afterwards, drawings of the parts and assemblies can be created, which are used for both inspection and manufacturing instruction. The software can also be used for generating animations to demonstrate machinery operation, performing thermal or stress analysis on components, creating highly detailed renderings of objects, and a host of other applications. If 3D scanning is used to digitize a part, software such as Geomagic Design X is required. This software is able to import scan data as a mesh. These mesh files can then be reoriented, combined to form larger meshes, and cleaned up to remove imperfections. Geomagic also has the option to perform parametric modeling in the same environment as the mesh, allowing a designer to quickly and accurately generate a CAD model for manufacturing reference. Scanned meshes can also be compared directly to a CAD model to inspect for physical deviations. If large quantities of parts needs inspection, more specialized software like GOM Inspect can be used to compare multiple samples at once and to perform more comprehensive deviation analysis. Other specialized engineering software includes programs like GearTrax. With this software, mathematically exact gear tooth geometry can be created that conforms to any existing gear standard. An engineer can take measurements of a physical gear, input the results, and have the program generate an ideal gear model, which is exported directly to SolidWorks. The program can also generate inspection criteria for part verification. Reverse engineering is the process of reproducing a product by examining its construction or composition. However, critical attributes of a product may not be apparent from just a simple examination. Knowledge of a product's function is critical to accurately producing a part that fulfills its intended role. The reverse engineering process begins with obtaining as much information as possible about a product. We work with customers to gather knowledge on a product's pricing, lifespan, intended function, mating components, and other factors. This information is collected in a variety of ways. Engineers may analyze photos or videos of a part in its operating environment. For more in-depth appraisal, engineers may be dispatched on-site to observe the operation of the equipment firsthand. If possible, an engineer will consult American Holt's continuously growing collection of OEM machinery manuals, which provide explicit knowledge on a part's function and mating components. These documents may be physical pages, digital PDFs, or electronic drawings. The most useful form of reference is a physical assembly containing the desired part. An engineer can use such an assembly to study part function, measure mating components, and test fit between parts. Aware of a product's context, an engineer can begin to take measurements, knowing which part features need to be scrutinized. An external cosmetic chamfer can be quickly measured, but a mating feature like a rotating shaft will require precise quantification. Once all measurement values have been taken, an engineer must use the values to interpret what original dimensions the part was designed for. For example, a feature that measures 0.497 inches was likely designed as a half an inch. With information on a part's function and its mating components, an engineer can verify these values and apply proper tolerancing to a part's features. For instance, if a hole is designed for a press fit, engineering principles can be used to identify the exact tolerance values required to ensure a proper fit for the hole and its mating pin. Additionally, knowing the manufacturing processes used to create a part facilitates its digital recreation. All of these factors combined allows for a robust and comprehensive engineering drawing, ready to be used in manufacturing. Designing a product is a complex process, but there are even more steps after the initial design. A product must be scrutinized both before and after it has been manufactured in order to ensure the highest level of quality. At American Holt, we apply rigorous validation and inspection processes for all parts we produce. During the reverse engineering procedure, an engineer uses measurement equipment and design principles to create a drawing that will serve as the instructions for manufacturing the final product. Once finished, the drawing is submitted to a supervising engineer to review, to check for completeness, good design, proper tolerancing, and other factors. The drawing is then passed along to the quality assurance department, along with the original sample of the part used to create the drawing. Inspectors take comprehensive measurements on the sample to ensure that the dimensioning and tolerancing in the drawing aligns with the real-world values. The process of going over the blueprint twice is resource-intensive, but the engineering adage states, measure twice, cut once. When the drawing is approved, it is then used to manufacture the final product, after which the product is brought back to quality assurance for incoming inspection. Here, the parts are measured against the drawings to verify that they have been manufactured correctly. Advanced systems may be used, such as automatic CMMs, video imagers, and 3D scanners. Parts may also be physically tested against mating parts as a foolproof check for functionality, and full assemblies are inspected for completion. The end result is a product that is guaranteed to perform as required from the very first unit sold.
Thank you for taking the time to become familiar with our capabilities at American Holt. I hope you can tell how proud we are of the process we've developed here. We're always reverse engineering new parts for our catalog, so if you have any components you'd like to be buying for a lower price at a higher quality, we highly encourage you to contact us for an appraisal. Be sure to take a look at our online catalog too, because we may already have exactly what you're looking for. Our website is www.americanholt.com, and we're also found on LinkedIn and YouTube.